Well, okay, thank you, Inhi, for the introduction. It's a big pleasure to come to KAIST and to Jeju. It's my second trip to Jeju. Last time I come to Jeju, it's invited by Inhi. And yesterday I had this very good evening talk with Professor Zhang, Professor Kim. I think I enjoy I'm a little bit jealous to you on the research environment. So I think you are having the world top standard research environment. Our students in China, although they're doing a lot of TRB papers, they don't have this very good environment to kind of communicate with the world best professor. So it's a very, very good opportunity. And my background, you can see that there's a data driven, right? So I stay overseas for 8 years. I got my PhD from National University of Singapore. Stayed there for 5 years, and after that, I come to Australia. I was a lecturer at Monash University at Melbourne for 3 years. And back to that period, I was a colleague with Dr. Kim. So my background in the past mostly focused on the network modeling, operation research. But in the past 8 years, because of the trend of this AI-driven research, so I spend most of my research time and my energy on the data-driven models. So we may ask ourselves, what is the kind of opportunity and what is the advantage of data-driven model? So today's tour, after I finish this traffic flow model, I think you can understand why we need to use a data-driven model and what AI and big data can help us mostly, okay? So the topic is mostly on traffic flow theory. I would like to do a survey among you. So any of you who have taken the traffic flow theory class, please put up your hands. So, okay, more than half. Okay, so you understand this topic like microscopic traffic flow modeling. So we use kind of the motion behavior of the vehicles, and macroscopic traffic modeling. Okay, very, very famous macroscopic traffic modeling is a fundamental diagram. Okay, this model is proposed like 80 years ago in the 1930s. Okay, by this very famous and big professor Greenshield. Okay, I think you all know the Greenshield model for the fundamental diagram, right? In the following decades, nearly 100 years, so we have different types of traffic flow model. So for example, we have this LWR model, and we have the MFD. Okay, those new trends, new developments. But all this research can date back to the initial point proposed by Professor Greenshield. So back to the 1930s, when the private camera is just popular, okay, back to the old days. So Greenshield used this camera to take photos, take pictures of the moving vehicles. So we see that he must be a very boring person. Why? Because if you buy a new camera, you take photos of your girlfriend. He takes the camera to take photos of the vehicles. But because of this behavior, he found a very interesting phenomenon. Is that this line here, okay? The x-axis is density. The y-axis is speed. So he just found out that there is a trend between the density and speed. That means if the density is high, the speed is also getting much lower. Okay, you see that? So there's a negative proportion between the density and the speed. This is we call #1 scientific finding of traffic engineering. Okay, so we borrow different theories from mathematics, from economics to the transport area, but we all agree, it's a consensus that this finding is the most important scientific finding, the research finding in transport area. And that gives us this traffic flow theory model. So this is a flow. You can take it as an out-through of the number of vehicles. And this is the density. So you see different types of models. It's developed afterwards. Well, Greenberg model, Underwood model, okay, to better fit this data. Okay, we have data and use models to better fit this data. 2 weeks ago, there's a professor, Xiaobo Qu, He came here to give you a lecture. You remember him? Yeah, Xiaobo Qu. Yeah, the guy with less hair. I can say so because he was my PhD roommate. We all get a PhD degree in Singapore. Yeah, he's a very best friend with me. Can you tell that we are same age? Hair is very important, okay? For a middle-aged man. So Xiaobo in 2016, he published a very good paper on TR Part B. He found that all these models, you use a series to better fit this data. But there is a big problem behind, is that all these previous models, they don't consider the unbiasedness, which is not acceptable. For statistics, the most important, the key point is unbiasedness. So Xiaobo just considered about unbiasedness, and then he developed a new model. Okay, it's Qu model, right? Yeah. So this research is still the frontier, and it's very hot topic until now. But today, because we are focused on the new trend, it's like a new generation of model. So we don't talk about the good side of this fundamental diagram. We talk about the negative side. Only when you find the problem, you can make new contribution, right? So when you find a problem, you are more than half successful because you can always find a method to solve your problem. So finding the problem is the most important for the researcher. So we talk about this, this model, and we find 3 very key problems. I will deliver to you the 3 problems. So if you agree that this problem is not acceptable, then you will see the value of big data. You will see the value of data-driven model. Okay. So number 1 problem is that if you read paper, you can see there are piles of papers on the traffic flow model. So Green-Shield, Underwood model, all these models in the past 80 years, they assume one thing is equilibrium state. So when you read the paper, for example, Eddy's paper, Eddy is a very famous professor on traffic flow theory. So all his paper published at good journals, TR Part B, Transportation Science, have one assumption, is equilibrium state. So if you just take this assumption, you will be confronted by a lot of mathematical equations. But for me, when I see this assumption, I doubt about this assumption. So critical thinking, okay? I doubt this. So what is equilibrium state? That literally means you have a team, a flow, a platoon of vehicles, moving vehicles. So the speed and also the distance between the vehicles is not changing. You see, if you assume that you have 1,000 vehicles, moving vehicles, and the speed of this vehicle is not changed, also the distance between the headway, okay, between the vehicles is not changed, then you get equilibrium state. Can you imagine that? So only in maybe highway in US, in California, okay, people do not change lane. They do not speed up. They just follow your previous vehicle. So only in that case, equilibrium state makes sense. But nowadays, we use a fundamental diagram to analyze the urban traffic flow. So you can imagine in urban traffic flow, the vehicles are changing their speed all the time. Okay, the distance between different vehicles is changing all the time. So this fundamental diagram, I should get back to this. So fundamental diagram, you must know that there is a very famous equation. It's Q equals rho times V, right? Q is flow. Rho, what is rho? Rho is density, right? And V, what about V? V is speed, average speed, right? I teach this class in Australia. I always ask my student, what average speed? You know, we have different types of average speed. We have temporary average speed, we have spatial average speed, right? So whether it's spatial average speed or temporary average speed, can you answer that question? Yeah. I always tell my students, it's what? It's spatial average speed. But when I teach my students this, I doubt myself, why is spatial every speed? The textbook told me so, but I don't really understand. I just memorize it, okay? So this fundamental diagram, we will doubt about this. So Q equals rho times V, only if you assume the equilibrium state it holds. And another very important outcome is that when I read the textbook for traffic flow theory, they have this conclusion, is that you can use the speed harmonic mean in cross-section behavior to replace the space mean speed. Why you need something to replace the spatial or space mean speed? Because this value is not easy to measure. It's difficult to measure, so that's why they use this. When I read all the textbook, just like at your age, I learned the traffic flow theory at least 3 times. Undergraduate study, PhD study, and also. So I learned this traffic flow theory. I read all the textbook. They tell me this conclusion. But how come it's true? So after I do my own research, I just do a lot of derivation. I have 2 pages, okay, mathematical equations. I do all the derivation. I finally understand. Only if you assume equilibrium state, then this conclusion is true. So that means a lot of existing conclusion in traffic flow theory is problematic. Because in urban area and in a very chaotic system, the equilibrium state doesn't make sense. You understand me? Okay, that's the first problem, okay? Let's see that every one of you is Albert Einstein, okay? Albert Einstein is because he found the problems and then he can find a good solution. He is poor in mathematics, but he can get helper. So the most important capability of Albert Einstein is he can find problems. So now we just deliver the first problem to you, and let's see the second problem. Okay, second problem is that in traffic engineering studies, we have 2 different standpoints for data collection, 2 different patterns for data collection. One pattern is cross-section observation, okay? Dr. Kim will give you a lot of data by cross-section observation. So this is a very theoretical term. So what does that mean? That means you use sensors to get data, okay? Imagine there's a detection loop or some kind of gantry for traffic flow observation. So you have sensors at one point to take data, to collect data, okay? So for this cross-section, basically it means you focus on one location. So you compromise the spatial value. So you only focus on one spatial point, one location, okay? And you collect data for a certain time interval. You understand me? Yeah, so the space is compromised, only one point. But you collect data for 1 minute or 1 hour, and then you get all the data you need. You can measure the density and the speed, right? Yeah, so this is a cross-section. And another is instantaneous observation. So instantaneous is on the other side, okay? So you just focus on one time spot. So it's instantaneous. And for the spatial interval, you have a certain spatial interval. You get me? So for instantaneous observation, then at this particular time spot, you can measure the speed of all the moving vehicles and also the density of this traffic flow. Okay, so now very important question we would like to ask ourselves is Q equals rho V, which case? You get me? So Q equals rho V holds is for instantaneous observation or for cross-section observation. Okay. The answer is only if they are in the same physical context, then the equation holds. You understand me? So only for instantaneous observation, because if you take the whole traffic flow as a stream of liquid, you take that as a liquid, then the speed, average speed of this whole traffic flow section became the liquid, the speed of this liquid, and its density became the density of the liquid. You get me? And in that case, if you measure the flow rate in the front side, then Q equals rho V. Only in that case. So that's why we say, and that's why in the textbook you can find the V here is space mean speed. Okay, so here comes the problem. Because this instantaneous observation is very difficult to measure. I once attended a speech by this very famous professor, Sir Hugendorf. He's a big professor in Europe, in Delft. So Sir Hugendorf told us, I'm doing a lot of research on instantaneous observation. Why? Because my lab, we have a helicopter. So we just get on the helicopter and we collect data. I found a problem because not every lab has enough funding to buy a helicopter. So that's why we cannot get data for this. These days, you may use UAV to collect data for this, but it's still not common. It's still not enough to cover the entire city. So that's why on traffic flow study, we always use cross-section observation to replace the instantaneous observation. So we use the average speed measured by a loop detector within 1 minute to kind of approximate the space mean speed. You get me? So here you should use critical thinking. I doubt about this theory. Is that, are they the same thing? Can you just use this temporal average speed to approximate the space mean speed, average speed? The answer is no. Still, if it's a equilibrium state, they are the same thing. But in urban area, the vehicles are changing. The vehicles are changing their speed all the time. So statistically speaking, they are not the same term at all. So if you use this replacement, later I will show you, the error could be 50%. That means it's a very, very big mistake you are making here. Okay, that's problem 2. So you should not use any inaccurate approximation. And that's a problem of traditional models. Okay, so let's come to the third problem. The third problem is very easy to understand because I'm working on the big data side. And these days in the urban area, the local land transport authority provide us with different kinds of big data. We have more than 30 types of big data. But for your traffic flow theory model, how many types of data you can use? They can only take use of at most 3 types of data because there are 3 terms, right? Q rho V, good morning. Q rho V, and the Q rho V, you even have mathematical functions to build a connection between them. So actually there's only one decision variable, which is speed. Okay, so when you get the speed, you can just calculate the density and you can just calculate the flow. So there's only one variable. So we have 30 plus different types of data, but your model can only take 3 variables. That means you are wasting at least 27 types of data. You get my point? So our previous modeling framework is not power enough to handle the data. The whole framework is just not able to accommodate other different types of data. So for example, you have the
the data of the weather, the data of the geometric design. So all those other type of data can just be used to measure the speed, to measure the density. So why not just take use of the real data itself, other than this kind of analysis or approximation? Okay, so this is problem 3. Have you followed the 3 problems? If you follow the 3 problems, you will understand that later, although I build a very complex mathematical model, but actually my initial point is from these 3 problems. Okay, once I detected the problem of this model, I can build my new model. So once you find the problem of existing studies, you know that a new generation is coming. You can develop a model and you can name it after your own name, Kim model, because we found the problem. Okay, so let's come to the data-driven model itself. The data-driven model, it's very straightforward in terms of mathematical formulation. So we can develop a data-driven model just like this. All kinds of machine learning model can be easily represented by this kind of simple formulation. X here is our input data. We have different types of input data, and the Q here, I take the flow as a label. But actually, you can take any other type of data or variable as a label. Okay. Here for data-driven model, the most important is to find a simple F. So the F can better fit your data. The F can give you a better prediction. That's a good model. Okay, so we just come to our new theory, and the new theory is quite straightforward, and the new theory can overcome all these existing problems of traditional model. Okay, so here for our theory, we first focus on demand side variable. So we find all these variables related to traffic flow itself. For example, the speed, the density, and all other features of the traffic flows. So we focus on the density side variable, which is very straightforward, not a surprise. But we just ask ourselves, for traffic flow, have you ever thought about the supply side variables? Is the supply side variable affect traffic flow movement? The answer is yes. So your traffic flow, especially in the chaotic urban area, is largely affected by the traffic signal, by the weather, by the road geometric design, whether there's voice, whether there's median. It's a big factor to influence the traffic flow. So why not consider all these supply side variables as decision variables in traffic flow theory? That's a breakthrough we have made there. Okay, so for our traffic flow model, we just develop a model like this. So there's demand side variables and there's supply side variables, and there's Q. So what does that mean? That means previously, Dr. Yin He working on the traffic signal analysis. So you optimize your signal. You use vSim. Okay, Dr. Yin He also worked in PTV, the best software, the best simulation software in our area. So you use vSim, you use software to analyze different signal plan. You have 10 potential patterns, and you use vSim to analyze, to measure each of them. You find the best one. But there are maybe 1,000 other potential plans. You just don't have enough time to measure it. So what we do is that we take the signal plan as a decision variable in our traffic flow theory. In that case, we don't need simulation to measure a given plan. We can just use the traffic flow model to output the best signal plan. Okay, you get me? So that's actually a very initial trend of large model. You know, in 2023, what is the most popular AI model? You all know that. Chat GPT. You're using that on your thesis, homework, assignments. So Chat GPT, they have a lot of parameters, right? They have billions of parameters. So for traffic large model, a very initial trend, if we want to develop our own large model, is that we can increase the variable types. We can take the traffic signal, the weather, all those things. As long as it has impact on traffic flow, we take everything as our decision variables, as our parameters. So that's the idea behind large model. Okay. So, and it comes to this part. I take myself as a modeler. So I spend most of my time on the mathematical equations, on the algorithm. So actually, most of my time I focus on this part, from this slide onwards. But here, actually, what I want to deliver to you is that even though you can build a very complex mathematical model, the model itself is nothing. The model is just some already mature tools that you borrow from the mathematical disciplines. So what is the most important is your idea, is your critical thinking, is the problem you find in existing study. So as long as we find the problem, we have our idea, which is our modeling framework, then this part becomes very easy. This part you can definitely find someone good at mathematics to help you, just like Albert Einstein. Okay, so here, what kind of model can we use for data-driven problem like this? We have supply side, we have demand side decision variables, and we use the flow as our output, as our label. So what kind of model we use? If you read a machine learning textbook, so anyway, another survey, how learned about the machine learning models, like SVM, deep learning, right? TensorFlow. So you only learn about ChatGPT, right? Because it helps you on the homework. Yeah. So all different types of model, yes, you can use them. And people say that different types of machine learning model has this kind of black box property, right? So you use them and you don't understand them. You just call the TensorFlow. So my student, every one of them has a superpower. You know what is their superpower? It's just to call the package. Just call a package, algorithm library. So that's their superpower. Okay. In Chinese we say the how to say that? It's a package man. Okay, 调包侠 package man, right? Yeah, so it's their superpower. You don't understand the idea behind this black box model, but I can tell you that it's not important. It's not the most important thing. The most important thing is to get this framework. So the question is on my table. I need to find a suitable model to solve the problem. I don't use deep learning. I don't use SVM. I don't use linear regression. I use this Gaussian process. Why I use Gaussian process is because Gaussian process has this Bayesian viewpoint. Okay, so this Bayesian way of thinking, just we don't need to hold any strong assumption. You just go and see. For example, when you study the statistics, the most common problem you learn or you are challenged in statistics class is that you have black box. In this black box, there are red color and black color, a small balls. So how is the ratio? So if you use all this other type of model, you need to make assumptions. But for this Bayesian Gaussian process, you don't need strong priori assumption. You just do the experiment. You do the experiment, you just take the balls, and you take 5 balls, you take 100 balls, you see the outcome, you adjust your theory. Okay, so this is a good idea behind this Bayesian and the Gaussian process. I don't make strong assumption. So if you use deep learning, you use linear regression, the time you choose this model, you already have bias because the model itself has disadvantage. Okay, it's endogenous. So here we use Bayesian. And another thing I would like to highlight for our machine learning problem is that, you see, when we deal with machine learning, I don't know about your background, but I assume you all take this class called as operations research, right? Optimization. In Southeast University, we call it transport system analysis, but it's actually operations research. So here, machine learning, there is a very different way of thinking. Is that for machine learning, we just hack the complex itself. So we just take all the information from this complex model itself. Our model, our problem is of course complex, complicated, because it's not linear, it's nonlinear, and it's not convex. So if you use operation research, that means you need to use linear approximation. So you lose a lot of useful information. If you use convex optimization, you need to use quadratic function, or you use convex function to approximate this model. You lose a lot of useful information. So machine learning is that we use a black box theory, but black box model, but the good side is that we take all the useful information into our analysis. Okay? I'm a very mathematical guy, but I don't want to make it mathematical. I want to deliver the idea behind it to you. Okay? So let's then come to the Gaussian process. So how we build this Gaussian process of the deep learning, the reinforcement learning, you know, those methods, they have very basic and easy tools. So that the tools, the basic tools they use is very, very easy, but they have large number. So for deep learning, if you check the neural network, so the cell, the neural cell itself, is very easy to understand, to calculate. But imagine you have 10,000 cells connected together. It became something that human being cannot understand. Okay, so the idea, the fundamental tool is very easy, but if you build everything together, it gives you intelligence. So why ChatGPT can pass the Turing test is because you have a large number of models. Okay, it can just guide you to a changing point. Okay, so here we come to our Gaussian process. The idea behind it is very, very easy. But if you check a paper, you check a textbook, it will be a real torture to you. You will find it's very headache to read those papers because a lot of mathematical equations. So same story to me. Back to 5 years ago, first time I studied the Gaussian process, at least 2 months of my time is wasted. Why? Because I check everything from the internet. And in the internet, a lot of study materials for Gaussian process is wrong. A lot of error. People do not really understand the Gaussian process, but they write those blog. They write those papers, online papers. So the idea behind the Gaussian process, I can use 3 minutes to tell you what is the real idea behind it, and you will understand the most powerful and the most frontier machine learning tool, okay, we use nowadays. Okay, if you go to MIT, you go to go to Berkeley, okay, those top universities, the OR professors, the computer science professor, many of them work on the Gaussian process. Okay, it's very frontier. So the idea behind it is like this. Okay, let's start our tour. You have a very complex model. You see this dotted line here, gray color. Okay, people in the back, you can see the gray color, the dotted line. So that's your real problem. Your real problem is there, but you don't know it. Okay, because if you know it, then you can easily use some mathematical tool to solve it. So it's a black box problem, it's a complicated problem. You cannot get the real function. This real function is difficult to check. So mathematically speaking, so what do you mean difficult to check? That means if you have one feasible point here, it's very difficult to measure the objective function value itself. That's called check. Okay, it's very difficult to check. Number two, this type of function we call it black box property problems. It's very difficult to measure the gradient. Okay, you use the gradient to develop some efficient algorithm, but this problem just tell you my gradient is very difficult or even impossible to measure. So for this kind of black box type of problem, a very complicated problem, what we do is that we use this surrogate model. Okay, I don't have the surrogate word here. So now you understand what is surrogate model. So I imagine, I guess Dr. Chen working on traffic safety, you use surrogate model a lot. Surrogate model is a frontier of traffic safety and also traffic data analysis. So surrogate model means my real problem is too difficult to handle. I don't want it. So I use another model to replace it. This yellow color, it's called a surrogate model. So I use this yellow model to replace my real one. As long as this kind of approximation makes sense, that means I can use a new model with good properties to replace my previous difficult one. You get my idea? So that's called a surrogate model. So why we use surrogate model is because surrogate model has all these good mathematical features. It's easy to solve. It's a convex one, it's a smooth one, so it's like that. So the idea, the problem now turns to how to find this good surrogate model, the yellow color. So Bayesian optimization equal to Gaussian process, then build this theory behind. It's a very powerful theory, build this theory behind. So I waste 2 months of my time because a lot of study material is wrong about GP. And later, after these 2 months, I just summarize my own understanding about this, and it can be very easy to deliver. Is that Gaussian process just has one important assumption or definition. So this important assumption builds this mathematical high building. Okay. What kind of assumption is that? It assumes if 2 points is getting close, okay, then their functional value is also close. Easy to follow, right? Mathematically speaking, it has a name. What name it has? The name is Lipschitz continuous. So if I teach you, you need to follow Lipschitz continuity, then all of you maybe became very dozy, right? Get to sleep. But here, the idea behind it very easy. So this assumption can be kind of handled by kernel function. We use different type of kernel function. For example, RBF. It just assumes that two values, xi and xj, if they are close enough, then the difference approaches zero, right? So the correlation between these two values becomes higher, this value equals to 1. So use this very, very simple assumption to build the mathematical building. Okay. That's the idea behind. So if you clearly remember this assumption I tell you, and you go back to check the textbook, to check all this study material, you can understand, oh, that's the idea behind it. That's why we have this kind of formulation. Okay. So for this surrogate model, how to build this yellow color model itself is that we need to do some experiment. So the black color function is unknown. It's very troublesome to check the function value, but still I can do some. So I do experiment at these 4 points. It gives me the functional value of these 4 points, right? Yeah, the y-axis is the value of these 4 points. Then I know that at these experimental points, the true value of its objective function. So I just build a smooth, very complex. So we have a very complicated high dimensional model. But for this high dimensional model, we can do a projection to this face. Okay? If we do a projection to this face, it gives you us different signaling plan. How is the influence of different signaling plan to your traffic flow? You get my point? So traffic signal is not something that you use a software to measure. Just like ChatGPT, you ask GPT, we call it transportation GPT. You ask GPT directly tell you, okay, the optimal traffic signaling plan is like this. Because it gives you a better capacity. You get my point? So this is the idea behind. Of course, in practice, because we have thousands of different intersections, and the geometry, the physical environment are all different. You need a huge amount of data to build a good model, just like ChatGPT. Okay, ChatGPT itself, the modeling framework was proposed in 1972. So it took ChatGPT 50 years to overcome the Turing test. Okay, so we have a theory like this, but in practice, definitely you need to do thousands of different experiments. You need the data from all over the world. Okay, different cities, they all need to provide you with a good quality and sufficiently large data. So we have a model like this, and for the first time, it incorporates the supply side variable into your traffic flow analysis. Okay, so this is the number 2 finding. Number 3 finding is that, somebody may argue with us that you have enough budget, so you can use more variables. For example, you have 30 different types of variables because you have money. OpenAI has sufficiently enough budget. So it took OpenAI how many? Maybe $1 billion to just train the model itself. So somebody may argue that if I don't have enough budget, I only have $1,000. So how to deal with my traffic flow model? If I only have $1,000, I can only have 2 variables. I cannot have 30 variables. So in the 2 variable case, is Q row V the best plan? We want to find out. Okay? So what we do is that because we have a very powerful model, so we can control the number of variables itself. Let's see how is the outcome. If we only have one variable, based on the performance, which is the best, we find that if we only have one variable, occupancy, which is density, is the most influential variable. And second ranking is a mean speed, it's average speed. Okay, if you only have one variable, it assumes that density and speed are the most important 2. Okay, but let's see the second test. If we have 2 variables, then what is the best combination based on the accuracy? Okay, and it gives us the best combination is not density and speed, it's density and small vehicle ratio. That means in urban area you have 1,000 vehicles, but how many trucks in this 1,000 vehicles? That's very important. That's even more important than the speed. You see? So it gives us implication that even if you have less budget, not enough budget, you should not take occupancy, should not take the density and the speed as your function. The best function. Number 1 is density and small vehicle. Number 2 is density and driving behavior. This is a ratio of lane changing. Okay, this is ratio of kind of aggressive driving. So this is driving behavior. So this is very related to traffic safety. Okay, so this is the third finding we have. We also want to make the black box model more transparent. So how to make it more transparent? Usually in machine learning, they use gradient to interpret the importance of your variable. So in the gradient also in some context, it's not easy to measure itself, but you can use some tool to just approximate the gradient. So to estimate the gradient. So we use a gradient. In our case, we use a gradient to measure the importance of different variables. Smaller number gives you higher importance. Okay, so we found that the most important variable for traffic flow is density. This is occupancy, is density. Number 2 important is traffic signal in urban area. Number 3 important is speed. Okay, just gives us some kind of idea. This is my last slide. So the last finding we have. So people always challenging the machine learning researcher. So what is value behind? You can do a better detection. You can find a more complicated model. So what is value? Apart from taking more electricity. So ChatGPT, spend a lot of power, $1 billion on training the model itself. So what is the value behind? If you are working on big data, you want to find a job in future as an AI-related, AI-aided engineer. So you should give a very straightforward answer to this question. What is the value of machine learning? The key value, the most important value, is accuracy. you should give a very straightforward answer to this question. What is the value of machine learning? The key value, the most important value is accuracy. Accuracy. So why we needed a large language model, NLP model, is because it can replace, it can just help us to get rid of some very low level job, very low level and stubborn job. Okay, so because the machine can do things as accurate or even beyond the human being's capability, then it's reliable. So when you answer this question, how come you have a better model? Why machine learning is important than my traditional convex programming or my bi-level model? You should directly give this very, very key answer, which is accuracy. Okay, so we did a test, which is falsifiable. Falsifiability is very, very important for transport studies because some of our previous theory, four-step model, the user equilibrium, although the theory itself is very complicated, it's not falsifiable. It cannot be tested in practice. That means it's not science. It's not real science. Okay, so it must be falsifiable. It must be okay to test. So how to test our model? We use fitness as a very, very simple test. Okay, the fitness itself is objective, is reliable, is falsifiable. Okay, so if you collect real data and your data is reliable, you find that the green shirt model, the fundamental diagram model, the fitness error. We're not talking about some other complicated task like prediction, like planning. We're talking about the fitness itself. The fitness error is higher than 20%, which is definitely not acceptable. So 50% means purely random. 20% you spend so many energy, you spend 80 years on a theory to kind of refine the model, but the fitness error itself is higher than 20%, which means the model itself just lose 80% of useful information. Okay, so fitness error, if we check the Gaussian process, our model, we haven't really fine-tuned the parameter. So just the initial model itself, the fitness error is lower than 3%. It's 10 times better. So you get the point behind? Yeah. So if you have a powerful tool, then this tool can just underpin your even more complicated task. So once you want to handle a very complicated task itself, for example, in urban area, transport planning and the area-based traffic signal control or area-based traffic safety evaluation is a very, very challenging task. So for a complicated task like this, you need to use a powerful tool. Otherwise, the model itself will just lose more than 20% of your useful information. Okay, with that, I finish my presentation. Actually, we come a long tour to talk about the Gaussian process. We found the problems behind traffic flow theory. Usually, I don't spend much time on the mathematical part. And today, what I want to deliver to you is critical thinking and the idea behind. So even though you have different background, hope that the idea can help you to better deal with your own problem. For example, if you are working on network planning, you're working on the congestion pricing or the taxi sourcing, okay, those very frontier or shared mobility. You are working, of course, autonomous driving. If you are working on those problems, as long as you find your problem is not linear, is not convex, it's very, very complex, then you should realize that I can use surrogate model. I can use a machine learning related model to help me better solve my problem. How come it can better solve your problem? Because it has higher accuracy. Okay? So this is the idea behind. Hope that this idea can help you with your future research and future job. Okay, thank you.
Very informative lecture today. That's great. Is there any questions from the audience? Yes.
So thank you, Professor Liu, for a very comprehensive presentation, especially starting from like the current limitation for the existing method and why for the existing for the more traditional method, and then why you come up and going through the more data-driven method. So I'm just curious when you talk about the Gaussian process, right? So how do we know if we can sample 2 points that are close enough, or how do we know if we have enough data so we can cover the entire space, considering you have a very high dimensional, like 30 variables?
Yeah. This is a very good question from a real expert. So we encountered all the problems Dr. Chen has mentioned. So today, because I'm in a stage with this young folks, okay, young generation. So I focus on a very easy to understand problem, which is fitness. But actually, I can send you our paper, recently published paper, one at TTD. So we encountered all these different problems. Let me go back to my visual aids. Okay. So we encountered several types of problems. Let's see this one. Another problem besides the fitness is that if 2 points getting quite close, that's your question, then the problem, the whole method is undermined. Why? Because for this problem, you use all types of matrix to help you on the calculation. And for Gaussian process, if you're familiar with the calculation, you know that more than 90% of the calculation power is spent on the matrix multiplication and the matrix inverse problem. So for matrix inverse, each row and each column is actually one data point. If 2 data points getting closer, so this matrix will be non-singular, because 2 different rows, they are too related to each other, linearly too related to each other. So in this case, the problem cannot be solved. I haven't prepared my slides, but I just describe it, okay? If 2 points can be very close, then the surrogate model will oscillate, and also impossible to use. So how to solve that problem? We use some mathematical tool to just replace the previous matrix inverse calculation. How to do that? I try to describe this in a short time. Is that if you have 2 points, they are actually 2 vectors. So you have do I have a pen or something?
Pen? Sorry, no, don't have one.
So imagine I have a pen, okay? So 2 points. This is a vector A. Vector A is like this, okay? And you have another point which is quite close to vector A. Is vector B. Is like this. Vector A and vector B are quite similar because they're close. So if you directly use vector A and vector B to do your calculation, it will become non-singular. So what we do is that we do not take vector A and vector B. We take vector A and vector B minus A. Because B minus A is somewhere here. It's quite different with vector A. So in that case, you can do your calculation easily.
You get my point? Yeah, so some kind of mathematical tools we use there. Of course, and it turns out the fitness outcome can be much better. The error is 10 to the power of 10 times lower. 小了10个数量级 10 to the power of 10. Okay, so it's much accurate. And we do this, all these kind of mathematical tools, but what I want to emphasize here is that anytime you want to do some kind of surgery to your algorithm, you must mathematically prove it. So we just propose 5 different propositions to just mathematically prove it, and then we are confident that we can just use B to we use A minus B to replace B. Yeah. So this is, I think, to your first question. Another problem to your second question is a very tedious one. If your number of dimension is beyond 30, I think is a milestone. If it's beyond 30, then your problem also becomes very difficult to handle. So what we do is that, in Southeast and also back to Singapore, a very key study area of our group is parallel computing. So we use large scale computing, high performance computing. So if you use 1,000 thread to solve this problem, then you can just go beyond 30. You can handle maybe 3,000 dimensions. So you need to use this high performance computing. Definitely for any of your traffic flow problem or autonomous driving problem, you need to just convert your problem into matrix. And with this matrix related problem, you can use GPU to solve it. So high performance computing is actually our answer to your second question.
Yep. Anything else? Yeah.
I think it'll be a wide range of questions in today's lecture, but my question is derived from the previous point mentioned in PT. It is difficult to maintain an equilibrium state of traffic flows in reality. Yeah. So if you want to construct an environment in microscopic simulations that is identical to reality, we often model driving behavior, implement flow for a group of vehicles, estimate queue lengths and add other index variable and parameters or something among various factors. What do you consider to be the most critical traffic conditions? Factor in implementing traffic flow to be close to reality.
Okay. Good question. I don't know whether I fully captured your question, but let me just answer your question first, and if not, we can just further communicate. So for your problem, your traffic flow model, you use it for what kind of objective? For autonomous driving or for mixed traffic flow? For what kind of problem?
Mixed traffic flow.
Mixed traffic flow, right? You have buses, you have large vehicles, you have
Yes,
small
yes,
vehicles, right?
yes.
For those kind of models, initially, because today our topic is actually macroscopic. We didn't focus on microscopic. So for microscopic, we find a very similar problem is that you use some simple rules to describe the vehicle motion itself. Basically, two most important ingredients. One is the following behavior, one is the lane changing behavior, right? So for these two behaviors, you use Newton's theory to just understand and also control the vehicle motion. Then you use this rule or you use this outcome to just apply it to all the different cases. That gives you a problem. So one model maybe is suitable for a particular case. For example, for autonomous driving, the mixed traffic, now the most popular model itself is IDM related model. If you go to Sumo, you find that it gives you 24 different types of car following model. So IDM is the most recommended. So you use those models and you use different parameters. For a particular case, maybe it's okay. But you cannot, you definitely cannot find a golden tool that can be applied accurately to all these different cases. So my recommendation is that you have sufficiently amount of data, you cover different scenarios. The scenario definitely, you drive yourself and you stay in a vehicle, you can see that we have different situations, different cases, different environment. So that gives you maybe 10,000, 10 billion different scenarios. One model just cannot cover all these cases. So my recommendation is that, okay, you get this data and you develop a powerful tool, just like Gaussian Process. It directly incorporate all these cases. It helps you to make a better decision. So if we talk about the logic behind, if we talk about how to publish good paper, maybe you want to make your theory more communicative. You want to develop a particular model for each particular question. But if we're talking about practical use, during the implementation, you just cannot judge which model is more suitable. So you need a more powerful tool, just like GPT, to help you. That's my answer.
Oh, thank you very much. Yeah.
Yeah, that's very good. Question and answer. More questions? Yes.
Oh, hello, I'm Sungmino in KAIST, and thank you for your great presentation. It is very interesting, and I have tried to learn and apply the fundamental traffic theory, but it is very difficult. So, I have one general question on how should master or PhD students prepare to conduct mathematical modeling research in transportation engineering. It is difficult to find the suitable idea of a modeling technique or a data collection method for their research topic.
Okay.
Yeah.
Thank you. Very good question. What about you? You are a master's student or PhD student?
I will go to PhD student. Yeah.
I thought so. I think so. So at a young stage of PhD, you always think the idea is the most important. How to find the idea, and also what is my future. I think his introduction is very, very important to you. You know, as a lecturer who have seen different types of students, different generations, I think very, very important thing is just to focus on your current step. You know, if you find your current step is interesting, you feel that your current environment gives you powers, and you just focus on the current step. So I think in his introduction is a good answer to your question. It's a big question. So how to use a mathematical tool and how to find a good research idea. I think until now I don't have the best answer. I'm not satisfied with myself in terms of how to find the research direction, how to find the best idea for publication. You know, although we publish a lot, but we're not that satisfied with most of our ideas. I think the key point behind it is that you try to aim high. You know, Elon Musk, why people support him? Because he has this very good fantasy tale story that they want to take people to Mars. So we support him not because he's good looking or something, because he's great. So I think aim high is very important. So you aim high, you want to be a real researcher that solve real problems. So these days, if you check the publication, even at the top tier journal, you will find that more than 50% of the publication is useless. Maybe they focus on the mathematical side, but it's not a real mathematical problem. It's something that he just, in his brain, it's not real. So it's not valuable because people take publication as the most important motivation. That's wrong. That's just wrong. It's a waste of time and also not good pathway towards success. So aim high. My current aim is that I'm doing operation research currently, and I'm currently doing machine learning. So a very interesting idea is why not just merge the two? So we take current technology
And those problem definitely has no clear answer. You just don't know how to solve it. You are in the middle of nowhere. But that problem is, if you spend your energy on it, then it will give you big outcome. Okay. That's my answer to your second question. To your first question is how to use the mathematical tool and also the computer algorithm. I think my suggestion back to nearly 20 years ago when I started my PhD is that you may find there are a lot of study materials, and you always want to start from the easy one. You think the initial step is easier, but that actually is a waste of time. For example, my supervisor, the first month of my PhD, asked me to study the book by Professor Shifi in MIT, okay, the Urban Transportation Networks. So I read this book in English. It's too troublesome for young student to read all those everything in English. So what I do is that I just fly back to China. I go to a Chinese library. I borrow a Chinese version of that book. So I read that book for 2 months. Initially, I feel very happy, but later I found it's a very lousy translation. I didn't know. So my suggestion to you is that you read the best thing. If you want to learn the OR, then you borrow the book from your library. Definitely you have it. It's a nonlinear programming by Professor Bazar, a linear programming by Basikus from MIT. So you read those classic things. You spend your time on it, and you dip yourself into it. Maybe initially, it's very struggling. For example, for my case, the time that I get rid of the Chinese version of the book, I come back to the English version. For the first week, I only read 2 pages. I spent all my time on it, but a lot of terminology I do not understand. So I need to just go to another book to understand, to check the terminology. So initially, it's very, very slow. But the second week, I finished 10 pages. And the next week, I can finish the chapter. So it became faster and faster. So it gave me the real power, true power to do my work. That's my sense.
Very
So normally, when you have a PhD student, you recommend some good books to them to read, to understand.
Yeah, classic books.
Yeah, so they can follow up your research, right?
Yeah.
So those 2 books are very classic books.
Yeah.
You recommend. What about the algorithm?
The algorithm, yes, actually,
The programming, actually. You have an algorithm that you need to know programming.
yeah. Programming as in practice is more important. And I always stay in the online platform of the engineer. So we talk and we just chat with each other. I think programming, the logic behind is very important. You need to train yourself first for logic, and the logic you also need to go back to the mathematical problem. So you understand the algorithm. This is number 1 important issue. Number 2 important issue is that you need to put your hand into the dirt itself. So if you want to be a good programmer, definitely you need at least 1,000 hours. That's my experience. So I spent 4 years for my PhD, and more than 2 years and a half I was programming. So to do this type of research, you definitely need to put your hand into the dirt.
So these 2 things are something different, right?
Yeah.
You do the maths, and at the same time, you need to train yourself to be some programming as well.
Programming.
Yeah.
Very important.
It's hard. Welcome to hard work. Yes, go ahead.
I have questions.
Yeah, please. You pass the microphone.
Thank you for
Introduce yourself.
okay.
Your masters?
PhD student. I'm a PhD student and I'm a Dongmin Kim and I'm a KAIST of Kite Chang Lab. And thank you for your great speaking. And actually, I have questions about the simulation-based experiment setting. Honestly, when I use simulations like a BCM or Sumo, I'm just wondering what the generalized road network is on this kind of study. So, is there some device for it?
Yeah, yeah. Good point. Very good point. Actually, I'm more like overall side of training back to my PhD study. But when I come to my current job, the job position required me to kind of get funding to expose to the industry. I find that the engineering type, the data-driven type of study is quite important for transport engineering. So I encountered the same problem. So you have, for traffic engineering type of problem, you need to use tools. And every tool you use, as long as you choose the tool, you are confronted by this kind of parameter setting, by how to use this tool, right? So it's a very tedious task and it's a challenging task. Until now, how to set the parameter and the environment, the best answer is still hyperparameter timing. It's still simulation-based optimization. You know, you see that you are working on the simulation-related works, so you must understand what is simulation-based optimization. SBO, have you learned that before? You should, I think not, maybe not. It's very frontier and it's definitely very, very powerful and important. So go back to Google this term, simulation-based optimization. You will find that for SBO, do you know which is the most modern method? It's Gaussian process. Yeah, so Gaussian process actually helps you to better set your problem. Because for racing simulation, your parameter is basically a black box problem. The black box problem is this green color function. So you want to find the best one. The best one, if it's autonomous driving, you want to know which is the most risky road environment. Only in that case give you more valuable research outcome. But I don't know which is the most risky one. Although I have my evaluation index, I don't know what is the best parameters that gives me the optimal index value. So how to do that? You need Gaussian process. You need to do simulation-based optimization. So if you do that, you make your work just enhance to another theoretical level. So what people do previously, for example, 10 years ago, Ian and myself, we were doing our, at a very young stage, doing our kind of evaluation problems. We just use WSIM with 10 different parameters. And for each pattern of parameter, we need to run the simulation maybe 10 times or even 100 times because it's stochastic. So in that case, your problem is experimental. It's not theoretical. So if you use a method, a tool like this, you then is very confident that my setting, my output setting is optimal. It's not something that is best among my current experiment. It's theoretically so.
Thank you very much.
Yeah, I agree with that. I think the Gaussian process is a very good tool to calibrate all the parameters in this thing.
Yes, well, yes. Yeah. And remember, I told you, every young generation, you have superpower, right? Techie man. So your problem, I think if you learn all this TensorFlow, you learn from Dr. Kim, okay, you can just write maybe 20 lines of code, okay, to solve a problem. It becomes a very straightforward task.
Any more questions? I think that's enough. Thank you very much for your